Thanks. Yeah, this is a work in progress that I've done with some of our student interns, in this case, Anders Quigg, and basically a project to investigate some tools for effectively visualizing the geometry of transcranial FUS. And there's certainly lots of visualization tools out there, but these are kind of our three leading reasons to do this, and one is that we need to communicate the complexities of this technology to a lay audience oftentimes, and having something to show that's interactive and visual is better than a complicated explanation. We also intend to use this ultimately as the interface to several groups that are pursuing full acoustic simulations for specifying targets and geometry. And then ultimately this may grow up into a patient-specific screening, planning, and review tool. Edward Tufte speaks for himself, but again, showing is better than telling, and the richer and more compact that showing is, the better. But we're also warned by Lars Lexile, and I think also Grady Booch, that no matter how pretty our pixels are, it's no substitute for clear thinking. So here's what this looks like. In collaboration with Insight Tech, we've modeled the Xblade neuro in both of its frequency variations. This here's the 650 and then the 220. And the focal spot and the steering volume. And we'll take away the MR model and just leave a ring representing the MR bore. So we can pick targets. It's a little hard to see probably on the projector, but the main view shows a slice through a registered 3D CT and MR data set. And over on the right in the MPR views, I'm picking a target, which then basically moves the focal spot of the transducer to where I'm pointing. And because this is 3D, I can resample this on any plane I wish, and it's always centered on the focal spot and showing a plane that's always normal to my viewing direction. And of course show it in 3D with some volume rendering. And again, I'll slice back down to the focal plane, the same kind of deal. Okay, so that's how we can pick particular places to put our focal spot in the context of this. So now for every, I'm going to put the target back on the VIM here, but for every element in the array, about 1,000 or so, using the GPU, I can trace a path, including the refraction on the outer and inner surface of the skull, and do this basically interactively. So here I'm going to drag the focal spot around. So where the rays strike the outside of the skull greater than the critical angle, they basically turn red and don't propagate. And you can see the colored bar on the bottom is showing how many effective elements are left, minus the ones that are higher than the critical angle. And it can show this in 3D as a series of spots where those beams intersect the outside of the skull and color code them by their incident angle. And here I'm moving it around, in this case anterior and posterior, and you can watch those spots move around and change color, and left and right. So and again, this is all interactive. You can drag this thing around in real time. And if we pre-compute that, that was individual spots. If we do this in a big sampled volume, we can present it as a 3D map, essentially, where green here represents places where I have 700 or more of the 1,000 elements with incident angles below the critical angle. And maybe calling this a treatment envelope is a bit of an overreach. It's certainly an element of that. And here we can actually see where that envelope strikes the base of the skull. So again, those maps are only taking into account the incident angles on the outside of the skull. There's no absorption, scattering, SDR effects or anything like that involved here at this point. That's why we ultimately will hand this off to an acoustic solver to get a real pressure field, but it's a good preview of probably the best case efficiency you might get for a given critical angle that you pick. And it's not totally dissimilar from what we've seen in skull phantoms and cadaver studies of treatment envelope heating. And finally, we haven't thought about it much for now because we're looking at targets in the middle of the head, but there is a frame involved in this geometry. If you start leaving the center of the head, that frame is going to start hitting things potentially. So here is just a mechanism for putting in, this is kind of an approximation of a Lexile frame, and as I move the target posterior, you can watch the pins and posts turn red. And if I turn I'll take the head out of there and do the opposite motion, you can watch it crash into the back of the transducer. So that's also an element, a merely geometric one, but still an element of the treatment envelope in terms of how far we can go before we physically hit things. So we'll have a live demo of this at the poster session for those of you who have interest and have questions about it. We intend to release this in some kind of usable form into the wild as open source this fall and use it as a tool for collaborating with acoustic simulation groups. And hopefully as we go along, it will grow up into something that might have some clinical utility. Thanks a lot.